Welcome. This is Fundamentals of Micro and Nanofabrication. I'm Swayam Prabha from IIT Bangalore. And in this lecture, we shall continue the general module on process integration. We were looking at how silicon solar cells get made at very large throughput and at very low cost. In the last lecture, we had started with the wafer. We had gone all the way. We have done diffusion, cleaning. We had finished deposition of the silicon nitride using PECVD. In this lecture, we shall now continue, see how electrodes get deposited, how the modules get made, and how the whole thing is put together into something you can sell to a consumer. So let's get started. So in the previous lecture, we had, as I said, we had finished PECVD. So this is what the cross section looked like. So you had silicon wafer. You have this orange layer, which is the doped phosphorus. The doping is on the both sides because you were doing this without any patterning. So there is a phosphorus on the back side too. And this phosphorus, as we shall later see, will go away, but for now it's there. And on top of the front surface, we have deposited another layer of PECVD silicon nitride, which is this dark blue color, and that is to prevent reflection of or reduce reflection of light. Okay. So now we have to deposit metal. Till now, if you notice, we have been very strategic. We have completely gotten rid of all patterning processes. We have not done one lithography step, and as you shall see in the rest of the lecture, we shall not do any lithography. Lithography is just way too expensive, and for 100 micron type features, lithography is an overkill. It's like trying to, I don't know, use a Ferrari to where a tractor can work. It's just not worth it to do a very expensive lithography systems and do 100 micron features. It just doesn't make any sense. So the industry sort of moved away from lithography to more scalable, cheaper, and other methods of doing patterning, specifically screen printing. Now, screen printing cannot do say anything thinner than 10 micron, maybe cannot do anything thinner than 20 micron. But that is enough for solar cells where the features are 100 microns, or these days around 30-40 micron. That is plenty. So that is what we try to do, and I will explain how a screen printer works and how do we get a pattern, and from then we'll understand how do we deposit a patterned metal. Okay. So this is what a screen printer look like. So what you have is you have a frame, and on this frame you attach a screen. So the screen actually has the pattern. So this is what the screen looks like. Okay. This screen has holes in strategic places and does not have holes in other places. So wherever it has holes, an ink can go through. Wherever there is no hole, the ink will not go through. How exactly is the screen made is given here. We shall come to it, but for now just bear with me. So screen has holes. Wherever there is hole, ink will go through. So then what you do is you attach that screen. You add some metal paste, and these metal pastes are metallic paste. So silver, aluminum. So we have pastes for these things. They are not fully formed metal, right? So they are sticky, viscous pastes. They are semi-liquid. What hope is that they have a whole bunch of organic materials that allow them to flow. The hope is that you would dry it, and after that you would cure it at very high temperature, and during that curing process all the organics will desorb out and leave behind the silver or aluminum, and that would make the metal contact. So that is how this process is done. So you have metal paste. This is a specialty product sold by specialty people, and so this is an important part of your technology, that which metal paste are you using. Okay. So anyways, you do that metal paste here. So that is what you see, this gray colored liquid that you see on the top, and then there's a squeegee, which is nothing but like a blade of some sort, and that squeegee is pushed against this screen and dragged from left to right. And that, as it is dragged from left to right, the edge pushes the paste through these holes in the screen and out, and then it gets printed on the substrate. So whatever is a pattern on the screen gets transferred to the substrate. So that's how screen printing works. If you zoom into the screen itself is nothing but a mesh. So it's just a steel mesh, and through these holes in the mesh, your ink will go through. Now, whenever you want to make a pattern, what you do is you add some of these ceramic plates of some sort which clog up the holes. So these holes are filled up, right? So because these holes are filled up, the metal ink will not go through, but metal will go through through the mesh which is exposed. How small can you print? You can imagine, like, the smallest you can print is some function of what is the smallest hole you can have in this mesh, right? If you try to print something smaller than this mesh opening, then of course it would not work, right? It would not look like a continuous line. It would look jagged and it would break. So the technology of printing, or the size, the critical dimension of printing, is decided by the mesh. Now, what is stopping you from making a finer mesh? A finer mesh provides more resistance for the flow of the ink. So then your ink must be more fluid. But the ink is fluid, then what will happen? It will go through the hole, get printed, and then spread out, right? It will not hold shape. So there is this fine balance where you want the ink to be viscous enough to hold shape, but at the same time not so viscous that it is unable to go through the holes. And while we keep pushing the technology, as the current state of the art is that you cannot print reliably below 30-20 micron. Most commercial Indian manufacturers that I know of tend to print somewhere between 30 to 60 microns. Okay, so that's the thinnest they can make. So that is what these lie. So these fingers, these are fingers as they are called. This is the thinnest line you can make. This is the critical dimension of your printing. There are thicker dimensions that you print, which are called bus bars. So, for example, if you zoom in, this is the bus bar area. This is the thicker bus bar, and this is the thin finger. And this thin finger gets translated to the finger here, and this thick bus bar gets translated to this bus bar here. So that's how pattern transfer happens without using photolithography through a squeegee and a screen printing machine. Okay. Let's get back to the solar production. So in solar production, what we are going to first do is we are going to coat the backside and make the back electrode. So what we do is we coat aluminum paste. So this is what aluminum. So aluminum is on the backside, and we leave some holes where we deposit silver. Okay. This silver is where we would actually make the solderable contact. The aluminum is our p-type dopant. Ultimately, this aluminum will form this p+ layer. This doesn't happen during the printing, because in the printing process it's just a liquid. This happens during the firing process, where this whole paste becomes dry and you form aluminum, and then aluminum diffuses. So P+ step will happen later. All we have right now done is coated this aluminum paste on the silicon wafer. You can actually see that this aluminum paste is wet, and so all you have is this printed aluminum. You still have not formed your back surface field yet. That will happen down the line. After you are done with this, then you deposit your AG. So this AG is the same thing as this. You also have to do the front side AG. I think I have another slide to show that. Yeah. So then you do the front side AG. So that is this structure here. Okay. This AG paste and this AG paste are a little different. Why? Because this AG paste must penetrate the silicon nitride to make contact with silicon. If you remember the lectures on diffusion, silicon nitride is a pretty good diffusion barrier. It's a masking layer. So you have to do something special to force the metal through the silicon nitride. And what they do is they add some grit, and through that grit, the AG paste is able to break through the silicon nitride and make contact with silicon. And by using this grit and breaking through, you once again avoid a photolithography step. You don't need to do any patterning. You just pattern the metal using screen printing and do the firing. And during the firing, the AG will go through the silicon nitride, make contact with silicon. You don't have to do any patterning on the silicon nitride separately, right? So you save a step. So this is another example of what a screen printing system looks like. This is an inline screen printer, so you can see that the wafers are coming from that direction and the wafers are going out in that direction. And within seconds, you're printing these patterns. You can actually see the front electrode patterns on here. You see no pattern here because it's yet to be printed, and this continuously keeps happening. Okay. So at the end of the day, you get some structure like this. Now remember, these are printed. They are still semi-solid viscous liquids. They have not dried yet. So first they are dried, and after dried they have to be fired to actually form the metal. Okay. So this is what you do through the firing. So you take these wafers and again you send them through a furnace, but this is called a belt furnace. Continuous inline process. Low cost, continuous inline process. They don't like batch processes. So the wafers go in from the back, the wafers come out from the front. And inside the whole long furnace, there is a whole range of temperatures, and this profile of this temperature is very precisely maintained. And during this profile, all the metal layers that we have deposited, the back AG, the front AG, the aluminum back surface field, all of these are cured at the same time, right? So it's not like we do one layer, then furnace, one layer furnace, one layer furnace. That would take too long. So they have optimized this all into one firing step will cure all the 3 pastes. Okay, so you do that, and when you do that, the aluminum back surface field formed in the back, and that is how you get rid of the orange or the phosphorus doped layer in the backside. You just override the phosphorus doped layer with the aluminum doped layer, which is a P+. So you have the P+, you have the P layer, you have the N+, you have the silicon nitride on the top, you have the aluminum on the bottom, you have silver contacts. Done. So that is how a commercial silicon solar cell is made. Okay. The other things to notice is that just wanted to highlight that how important small optimizations are. So here, for example, there are 4 different recipes that were tried in this furnace, where the temperatures in each of these 6 zones were slightly different. And with very small changes in temperature, you can actually get small changes in efficiency. But for a researcher, difference between 6.25 and 6.4 is minuscule, maybe not worth thinking about. But for a commercial fabrication system that is producing thousands of wafers an hour, any small increase in power is a lot of money on the table. So I think there's some, like each small efficiency improvement is worth a few $1 million or some number like that. Okay. Overall, this is what a structure finally looks like. If you take an SEM image, this is what the P-type silicon is. You have the front AG electrode, you have the batch aluminum paste. This is where the aluminum back surface field has happened, and this is your P plus junction. Okay. Here's what a commercial silicon cell looks like from the front and back. This blue tinge is because of the silicon nitride that we have deposited. You see the front electrode, you see the back aluminum surface field, the back AG electrode, and all of these different cells then have to be connected in series to actually make a module. And in order to do that, these bus bars are soldered. So one bus bar is soldered to the next, and that is typically done with these called tabs. So you see this tab, this metal wire that is connected to the wafer. So this connection is done on the bus bar. And yeah, so these tabs are then done, and each tab is connected to another, and you make a module. Now, before you go there, however, you have to do testing and sorting. So your thousands of wafers and hours are coming out. Not all of them have exactly the same efficiency. And typically in a module, all the cells are in series. What that means is they must have the same current. But if there are slight variations, they will not have the same current. And if you connect them in series without doing any sort of sorting, then you lose out a lot of the efficiency. So what people do is they sort of sort it in bins, the highest efficiency, next highest. The number of bins can be 16, 20. And in each bin, then you, before making a module, you would only take wafers from one bin. You would not mix and match. Okay, so yeah, the sorting can be done manually. In this case, this lady is doing the sorting. That can also be done automatically. Now there are these automatic systems which would measure the efficiency, calculate which bin it should be in, and appropriately store it in different holders. And yeah, so you have to do testing and sorting before. Typical modules are either 60 cell modules or 72 cell modules, though these days people have started making much larger modules. But the vanilla modules are 72 cells. So you need 72 of these 6-inch cells to make one module. Okay. Now what is a module? So module is just a structure that provides some physical support to these cells while they last, so they can work out in the field without getting damaged. And other day we are looking at what 180 micron thick silicon. It can easily get damaged. So if you look at the cross section, you would have these PN junctions, and they are all connected in series. So there must be a contact made from the top of the N-type to the bottom of the P-type, right? So these are the tabs that we discussed, okay? And you will connect 72 of these cells one after the other. That is just the electrical part. In order to protect them from the environment, you have the top tempered glass. Often this glass has some anti-reflection coatings on it also. You would have either a glass on the backside. The glass on the backside is there if the module is designed to accept light from both sides. Those are called bifacial modules. But that's not very common. The more common thing is the backside is just mechanical support. So it has some often Tedlar film. Tedlar is some polyvinyl fluoride. And between this glass and the back surface, there is a lot of space, right? It's a lot of empty space. You don't want to leave that empty space where the wafers can move around. So what you do is you fill it with something called a pottent. So this is what the pottent. The pottent is EVA. EVA is a plastic. It's a petroleum based product. A lot of the soles of your shoes, if they are rubber or plastic, they are probably EVA. Okay, so yeah, if you have cheap chappals or cheap shoes, it's probably EVA. So that kind of material, but of course we will use the one that does not have any color, it's transparent, it's stable. So you just fill the whole place with EVA. So all this yellow is EVA. Okay, and it just fills all the nooks and crannies and makes sure that the wafers don't have any place to move. So this is the cross section, this is the front section. So you see the aluminum frame, you see the front glass, you see the wafers, you see the encapsulant. This encapsulant is the EVA film. Then the back sheet, you see the bus bars, the individual wafers connected, and finally the electrical connections have to come out, right? So what you do is you attach a junction box, and the junction box is then connected to the wires, right? So that's what a wafer looks like. Sorry, the module looks like. And this aluminum frame provides some rigidity, so right, so it can withstand some sort of abuse while it's being installed. Okay, so that's what a module would look like. If you look at a zoomed out image, this is what module would look like. So you have the 72 cells. So 1, 2, 3, 4, 5, 6, 6 cross 12, 72. 1, 2, 3, 4, 5, 6, 6 cross 12, 72. Each of these modules is around 1 by 1.5 meters in size. And the multicrystalline wafers, because they have square shaped, when you make a module, they don't really have any dead space in the middle. So you see, it looks a completely filled, there's no white area. But the monocrystalline cell has this rounded pseudo square corners, right? So when you make a module, you can actually see these squarish or smooth square shapes that are left open. Now this of course is a loss, right? Because it's not absorbing sunlight. But there's nothing we can do about it, that's just the shape of the cell. So as the technologies have progressed, silicon solar manufacturers have tried to reduce the size of this dead space, but still in modern monocrystalline modules, this dead space still exists. So you can actually tell just by looking at a wave panel whether it's monocrystalline or multicrystalline just by the presence or absence of these holes. The monocrystalline cells also look little more darker, little more blacker because they have better texturing. Because as we discussed, it's very easy to form pyramids on those, right? Multicrystalline wafers don't have that good texturing, so they reflect a little, so they have this bluish tinge more of. Once again, you see the grain size in the multicrystalline cells, you don't see any grain size in the monocrystalline cells. Depending on different technologies, the number of cells, how much care you're using, what your process is, you can get typically 72 cell modules typically give out output somewhere between 300 to 400 watts. Mostly towards 300, 320 watts, maybe 340 watts. Rarely on the upper side of 400, that is if you have heterojunction or some other advanced technology. Alright, so with that we come to an end of this lecture. I just hope you get a sense of how, even though they are also still doing microfabrication, but solar cell does a very slightly different form of microfabrication, and how they were able to reduce cost, not use photolithography, do patterning in more traditional ways, and still get a very efficient and marketable electronic product. So yeah, something to think about. Thank you for your time, and I guess this is my last lecture in this course. So thank you for those of you who have lasted this long. Thank you, and I'll see you sometime later. Bye.